We spent the last several lectures discussing ways to calculate bolt and member stiffness, and I wanted to show you a finite element analysis model to validate the simple approximations we are using to calculate the equivalent stiffness of a clamped plate. And so what I've done here is I have taken two 15 millimeter thick plates. Top plate is made of aluminum. The bottom plate is made of cast iron. I've thrown a steel washer on the top of the plate, and I have thrown a steel washer onto the bottom of the plate. The washers are 3.5 millimeters thick. The plates are a large enough diameter that they can fully contain the frustum that is going to be generated by clamping these things together. Now I'm going to represent the bolt load that clamps the plates together as a pressure load that I am applying to the top washer over an outer diameter that's 1.5 times the bolt diameter. And the bolt diameter is 14 millimeters in this case. An M14 by 2 bolt that is used to clamp an aluminum top plate to a cast iron bottom plate. Both of those plates are 15 millimeters thick, and there is a washer at the top and a washer at the bottom. It's an easy thing for us now to use the method of Frustums to find the equivalent spring stiffness of this bolted assembly. I've left the bolt out of this because I'm simply going to represent the initial preload of the bolt through a force that is applied over this annulus right here. I go to the bottom side and I apply a constraint over the same sort of annulus, and the outer diameter of that annulus is 21 millimeters. The inner is 14, the outer is 1.5 times the inner diameter, the 14 millimeter bolt. The washer itself is 39 millimeters in diameter, but the contact pressure footprint runs from 21 to 14. Now I just fixed the bottom side instead of applying another load, and that allows me to run a finite element analysis on this assembly. And then I can use that finite element analysis to calculate a deflection and use the deflection and the known applied load to calculate the spring stiffness. And I have done this, and so I can actually show the results. The results are here. We find that the average displacement at the top side, and it's a total displacement, so it means it could have X, Y, and Z components, but it's not going to be that much different if I just choose the Y displacement. But if I do choose the Y displacement, you see that I get a downward displacement in the center of the load annulus of minus 0.01782. So I apply a load to the top side over the contact area of the washer face, and the bolt is applying that force to the contact area. Well, the force that I applied is something that we should look at. I should go over here and look at our load cases and show you what the load actually is. If I do that, you would find that I applied a structural load of 26,000 newtons over this contact area directed vertically downward. You already saw the displacement that I achieved is in the Y direction. It's minus 0.01782 millimeters. So how am I going to estimate a stiffness from this? Now remember, the load is equal to the stiffness times the displacement. The displacement is minus 0.1782 millimeters, and the load is 26,000 newtons. So if I divide that load of 26,000 newtons by this displacement of minus, well, not minus any longer, it doesn't matter, of 0.01782 millimeters, I can then calculate a spring stiffness. And if I do that, I will find a spring stiffness of 1,459 newtons per meter. If I use my spreadsheet to find an equivalent stiffness using the method of Frustums, for this particular assembly where I have a 3.5 millimeter washer on top, a 15 millimeter thick top plate that is made of aluminum, clamped to a 15 millimeter thick bottom plate that is made of cast iron with that cast iron modulus, and a steel washer again at the bottom, my calculated member stiffness is 1,543 meganewtons per meter. From the finite element analysis, I had an estimated value of 1,459 meganewtons per meter, a difference of roughly 5.8%. So this is good.